Hi everyone, welcome to my talk on big data in security. I will talk about how we can analyze these big data infrastructures to better protect them. Before starting, please let me introduce myself briefly. My name is Sheila. I work as Head of Research at DreamLab Technologies, a Swiss infosec company. I'm an offensive security specialist with several years of experience, and in the last time I have focused on security in cloud environments, cloud native, big data, and related stuff. Okay, so let's go to the important things. There are some key concepts that I would like to explain before jumping into the security part. Probably the first thing that comes to mind when talking about big data is the challenge of storing large volumes of information and the technology that will take care of it. Although that's correct, around the storage technology there are many others of great importance that make up the ecosystem. When we design big data architectures, we must think about how the data will be transported from the source to the storage, if the data requires some type of processing to be consumed, and how the information will be accessed, right? So the different processes that the data go through are divided into 4 main layers that comprise the big data stack. So we have the data ingestion, that is the transport of the information from the different origins to the storage place, the storage itself, the data processing layer, because the most common is to ingest raw information that later needs some kind of processing. And finally, the data access layer, basically how users will access and consume the information. And let's add one more layer here. This is not part of the big data stack, but we have this layer in all big data infrastructures. The cluster management is really important. So for each of these layers, there is a wide variety of technologies that can be implemented. The big data stack is hugely big. These one are just a few of the most popular technologies. For example, Hadoop for the storage, Spark and Storm for processing, Impala, Presto, Druid for accessing the information, Flume, Scoop for data ingestion, and Zookeeper for management, right? So when we analyze an entire big data infrastructure, we can actually find many different and complex technologies interacting with each other. They meet different functions according to the layer of the stack where they are located. So let's see an example of a real big data architecture. Here we have 2 different clouds, one in AWS and another one in any other cloud provider. So both are running some Kubernetes clusters that are serving different applications. So we want to store and analyze the log of these applications. For that we will use FlowMBit to collect all the applications logs and write them to Kafka for the first cloud, and stream them using Flume and Kinesis to an on-prem Hadoop cluster. Within the Hadoop cluster, the first component that will receive the data is Spark structure streaming. This one will take care of ingesting and also processing the information before dumping it into the Hadoop file system. So once we have our information here, we want to access it. So for that, we could implement, for example, Hive and Presto. Or instead of Presto, we could use Impala, Druid, or any other technology for interactive queries against Hadoop. If we are developing our own software to visualize the information, then we will probably have an API talking to the Presto coordinator and a nice frontend. So finally, we have the management layer. Here it's super common to find Apache Zookeeper to centralize the configuration of all these components, and also an administration tool like Ambari or a centralized log system for cluster monitoring. So this is an example of a real big data architecture and how the components interact with each other. So back to security, how can we analyze these complex infrastructures? Well, I would like to propose a methodology for this, where the analysis is based on the different layers of the big data stack. I think that a good way to analyze big data infrastructure is to dissect them and analyze the security of the components layer by layer. So in this way, we can make sure that we are covering all the stages that the information we want to protect goes through. So from now on, I will explain different attack vectors that I discovered throughout this research for each of the layers. Good, so let's start with the management layer. Zookeeper, as I said, is widely used to centralize the configuration of the different technologies that make up the cluster. Its architecture is pretty simple. It runs a service on all nodes, and then a client, let's say an cluster administrator, can connect to one of the nodes and update a configuration. So when that happens, Zookeeper will automatically broadcast the change across all the nodes. If we scan a node of the cluster, we will find that the ports 2181 and 3888 are open. These ports belongs to Zookeeper. The port 2181 is the port that accepts connection from clients. Should we be able to connect to it? Well, according to the official documentation of Femberry, a tool that is widely used for deploying on-prem big data clusters, disabling the firewall is a requirement for installing big data clusters. So we can probably connect to it. How should we do it? We can download the Zookeeper client from the official website, and then it's just about running this command, specifying the node IP address and the 2181 port. So once we connect, we run the help command. There is a list of actions that we can execute over the C nodes. The C nodes or Zookeeper nodes are the configurations that Zookeeper organizes in a hierarchical structure. So, with the ls and get commands, we can browse this hierarchical structure. We can actually find very interesting information about the configuration of all the components that make up the cluster, like Hadoop, Hive, HBase, Kafka, or whatever. And we could use it for further attacks. We can also create new configurations, modify existing ones, and delete configurations. And this will be a problem for the cluster. Some components might go down. Zookeeper, for example, is commonly used to manage the Hadoop high availability. So if we delete everything, the cluster might run into troubles. So I will not do a demo of this attack because it's pretty simple, but this is quite impactful. So what about Ambari? This is a pretty popular open source tool to install and manage big data clusters. It has a dashboard from which you can control everything, whose default credentials are admin, of course. but if they were changed, there is a second door that is absolutely worth to check. Ambari uses a Postgres database to store the statistics and information about the cluster. And in the default installation process, the Ambari wizard asks you to change the credential for this dashboard, but it doesn't ask you to change the default credential for the database. So we could simply connect to the Postgres port directly using these default credentials that are user Ambari and password big data, and explore the Ambari database. And there we will find these two tables, user authentications and users. So to get the username and authentication key at once, we need to do this inner join query between those two tables. So the authentication key is a salted hash. So the best thing that we can do here is just update the key for the admin user, for example. I dug into the Ambari source code to find a valid salted hash, and here we have the hash for the admin password. So now we can run an update query. And once done, we can log into the Embody dashboard with the admin credentials. I know this example pretty stupid, but it's absolutely worth to check because Embody controls the whole cluster. If you can access this dashboard, you can do whatever you want over the cluster. And as the default installation process doesn't ask for these credentials to be changed, then you can most likely compromise them in this way. Good, so the important thing in the cluster management layer is to analyze the security of the administration and monitoring tools. Let's now talk about the storage layer. First of all, it's good to understand how Hadoop works. It has a master-slave architecture and two main components, the HDF, that means the Hadoop Distributed File System, and YARN. The Hadoop Distributed File System has two main components, name that saves the metadata of the files stored in the cluster and runs in the master nodes, and the data node that stores the actual data and runs in the slave nodes. On the other hand, YARN consists of two components as well, the resource manager located on the master nodes that controls all the processing resources in the Hadoop cluster, and the node manager installed in the slave nodes that take care of tracking processing resources on each slave node, among other tasks. Basically, what we have to know is that the Hadoop file system is where the cluster information is stored, and YARN is a service that manages the resources for the processing jobs that are executed over the information stored. Basically, it's that. So when it comes to the storage layer, we are interested in the Hadoop file system. So let's see how we can remotely compromise it. Hadoop exposes an IPC port on 8020. So we should find this port open in the Hadoop name nodes. So if we can connect, we could execute Hadoop commands and access to the stored data. However, this is not as simple as the Zookeeper example was. Managed to do this is a little more complex. There are 4 configuration files that Hadoop needs to perform operations over a Hadoop file system. If we take a look at these files inside the name node, we can see that they have dozens of configurations parameters. So when I saw that, I wonder, if I am an attacker and I don't have access to these files, how can I compromise the file system in a remote way? Well, part of this research was to find among those dozens of configurations which ones are 100% required and how we can get them remotely from the information that Hadoop itself discloses by default. So I will explain how we can manually craft these files one by one. Let's start by the core site XML file. The only information we need here is the namespace. It's pretty easy to find this information because Hadoop exposes by default a dashboard on the name nodes on the port 50070, pretty high port, and we can access it without authentication. So here we can find the namespace, Sheila in my target cluster, and that's all we need for this file. Then we need to craft the HDF site file. It's necessary to know the namespace that we already have from the previous file, and we also need the names nodes IDs and the DNS of them. We could have 1, 2 or more name nodes, and we need to provide the ID and DNS for all of them in this file. Where can we get this information? From the same dashboard. We have the namespace and the name node ID and the DNS here. We just need to access this dashboard on each name node. Remember that it's on the port 50070. Another alternative is to enter the data node dashboard. It's on port 50075. And there we can see all the names nodes at once. Good. The next file is the map site one. Here we need the DNS of the name node that hosts the MapReduce shop history. We can try to access the port 19888 on the name node, and if we can see this dashboard, then that's the name node we are looking for. And we already know its DNS from the previous dashboard. Finally, we need to craft the yarn site file. Again, we need a name node DNS, in this case the one that hosts the yarn resource manager. To detect that, we can try to access the port 8088, and if we see this dashboard, then that's the right node, and here we can get the DNS as well. So all these dashboards are exposed by default and don't require any authentication, but if for some reasons we cannot see them, we can try to get this required information through Zookeeper with the attack I showed you earlier, because Zookeeper also has all this information. Cool, so once we have the configuration files we need, the next step is to install Hadoop in our local machine and provide it with those files to perform the remote communication. As I didn't want to install Hadoop on my local machine, I built this Docker file. Feel free to use it, it's pretty comfortable. Just change the Hadoop version to match the version of your target cluster, right? So from now on, this is going to be our Hadoop hacking container running on the attacker machine, right? So let's run it and get a shell inside it. And we can create a config directory to place the XML files we have crafted before. And you also need to copy these log.property files. Another thing I did was to edit the host file to directly resolve this name node DNS. You can use the IP addresses on the XML files, but I had better results doing this. Okay, so we are ready to go. Just pass through Hadoop this config directory and execute an ls command, for example. So voila, we can see the entire Hadoop file system from a remote attacker machine. So before jumping into a demo of this, I would like to mention that most likely we will need to impersonate HDF users. For example, if I try to create a new directory using the root user, I cannot do it. So we need to impersonate a user that has privileges within the Hadoop file system. So one of these ones. Fortunately, that's very easy to do. We just need to set this environment variable with the Hadoop username before the command, and that's all. That will allow us to for example, create a new directory. And we can also delete directories and files, of course. We could actually wipe out the entire cluster information. So okay, let's see a demo of this. So here I am in my container, and these are my files. This is the HDL files. I have to place the namespace in several places, and in this file you need to also provide the name nodes IDs and DNS. If you have, for example, in this case I had two, so I have to provide the DNS for the two name nodes. For the map red site file, we also need to provide a DNS for the map shop history, and this is the yarn file that also need to provide the DNS for the yarn resource manager node. So with that we can execute commands, Hadoop commands to browser the Hadoop file system. And if we execute the help command, we can see that there are a lot of common commands that we can execute, like copy files or remove files, most common commands that we can find in a Unix system. And here, while I'm making the impersonation for the HDF user, so I can create a new directory. And also I could delete the directory, of course. So basically, we can perform any operation over the Hadoop file system in a remote way because I'm executing it from a Hadoop hacking container that has nothing to do with the original cluster, right? Good. Okay, so let's jump into the processing layer and see how we can abuse yarn in this case. So back to the Hadoop architecture, just to remember, yarn takes care of the processing jobs over the data stored in the cluster. These jobs execute code in the data nodes. So our mission here is trying to find a way to remotely submitting an application to yarn that executes a code or command that we want to execute in the clusters node. Basically achieve a remote code execution through yarn. And we can use the Hadoop IPC that we were using in the previous attack. It's just necessary to improve a little bit our yarn site file. We need to add the yarn application class path property. This path used to be the default path in Hadoop installations, so it should not be difficult to obtain this information. In the example here, we can see the default path for installations using the Hortonworks packages. Then this other property is optional. It will specify the application's output path in the Hadoop file system. It might be useful for us to easily find the output of the remote code execution, but it's not necessary. And something I would like to mention that I didn't say before, if you can access these panels that we have seen, under /conf, we can find all the configuration parameters. But you cannot just download and use this file. We still need to manually craft the files the way we were doing it. However, if something is not working for you, here you might find what's missing. Here we can see that, for example, we can get the yarn application class path that we need. Okay, so now that we have improved our yarn site file and we can submit applications to yarn, the question is, what application should we submit? Here, Hortonworks provides a simple one that is enough to achieve the remote code execution that we want. It has only 3 Java files because yarn applications are developed in Java. But there are a lot of Hadoop libraries necessary to include and use, so it might not be easy to develop a native yarn application. But we can use this one for our purpose. It takes as parameter the command that we want to execute on the cluster and the number of instances, which is basically on how many nodes our command will be executed. So we will clone this repository in our Hadoop hacking container and proceed to compile this Java application. We need to edit the POM XML file and change the Hadoop version to match the version of our target. This is pretty important, otherwise this will not work. So remember to match the version, and once done, we can compile the application using Maven. The next step is to copy the compiled jar into the remote Hadoop file system. We can do it using the copy from local hdf command. And now we are ready to go. So in this way, we can submit the application to yarn, passing as parameter the command we want to execute and the number of instances. Here an example. I have executed the hostname command over 3 nodes. And we are going to receive an application ID. It's important to take note of it, and it's even more important to get this finished status. That means that our application was executed successfully. And now what? Where can we see the application output? Well, we can use this command, passing the application ID we got in the previous step. And the output is going to be something like this. As we have executed this command over 3 nodes, we have 3 different outputs for the hostname command. And of course, we can change the hostname command for any other, right? So let's see a demo of this. Here again, I have my files, and I have performed a little modification over the yarn file, right? And I have the simple yarn application. This is the Hortonworks example. And I already copied this file into the remote Hadoop file system. So the only thing I have to do now is just to execute it. And for that, we need to pass the local path for the application, the command that we want to execute, the number of instances, and the remote path of the shard. So once done, we get the application ID and the finish status. Good, so take note of that ID. In my case, I need to perform a copy just to allow shard to then find the output. So I just copy the output to a different folder in the remote file system. And now we can use the yarn command with the application ID to get the real output. So this is the output, and here we can see the output of the hostname command for Hadoop 1, the first node, Hadoop 2, and Hadoop 3, because we have executed it over 3 data nodes. And let me show just one more output of an application I ran before. So you can see, for example, I had run a command to dump the information of a file in the Hadoop machines, in the data nodes. So here we can get, for example, the password files. Good. So basically we can achieve a remote code execution using yarn. The yarn will always be present in Hadoop clusters. And if we want to modify that yarn application is quite simple. We could modify it to perhaps execute a more complex command. Just keep in mind that any changes must be made in both the application master file and the client file, right? If we want to get something like a reverse shell on the cluster node, it's possible, but keep in mind that this is a shop process that starts and finishes. So we might need to use alternative like backdooring the cron tab with the yarn application, for example. So you could modify the application to run this specific command. When you submit the application, it will execute this backdoor for the cron tab, and then you will have a reverse shell in the data nodes. This is just an example, right? Okay, I can't help but talk about Spark in this section. Spark is a super popular and widely implemented technology for processing data. It's generally installed on top of Hadoop, and developers make data processing applications for Spark, for example in Python, using PySpark, because it's easier than developing a native application for yarn. And also Spark has other advantages over yarn as well. So Spark has its own IPC port on 77, and we could submit an Spark application to be executed on the cluster through this port. It's easier than with yarn. Here we have an example. This small code will connect to the Spark master to execute the hostname command on the cluster's nodes. So we have to specify the remote Spark IP address, our IP address to receive the output of the command, and the command itself. Then we can run this script from our machine. We don't really need anything else. It's pretty simple. But I'm not going to talk in depth about this because there is already a talk 100% dedicated to Spark that was given at DEF CON last year. I truly recommend watching this talk. The speaker explains how to achieve remote code execution via Spark IPC. That is the equivalent of what we did with Yarn. So keep in mind that Spark may or may not be present in the cluster, while Yarn will always be present in a Hadoop installation. So it's good to know how to achieve remote code execution via Yarn and also via Spark, if we have the possibility to abuse this technology as well. Awesome. Let's take a look at the ingestion layer. If you remember from our big data architecture example at the beginning of this talk, we have sources of data, and such data is injected to our cluster using data ingestion technologies. There are several ones. We have some designed for streaming, like Flume, Kafka, and Spark structured streaming, that is a variant of Spark. And then others like Scoop, that ingests static information, for example, from one data lake to other data lake, or from one database to a data lake, and so on. So, from a security point of view, we need to make sure that these channels that the information goes through from the source to the storage are secure, right? Otherwise, an attacker might interfere those channels and inject malicious data. Let's see how this could happen then. This is how Spark streaming or Spark structured streaming works. It's a variant of Spark that injects the data and also processes it before dumping everything into the Hadoop file system. So it's like having two components in one. And Spark streaming, it works with technologies like Kafka, Flume, and Kinesis to pull or receive the data, but it also has the possibility to just inject data from a TCP socket. And that could be very dangerous. Here we have an example of how the code looks like when the streaming input is just a TCP socket. It basically binds a port on the machine. So abuse this is super easy. We can use a netcat or our favorite tool and just send data over the socket. And it works. But what happens to the data we inject will depend on the application that processes it. Most likely we will crash the application because we might be injecting bytes that the application doesn't know how to handle. Or our bytes might end up inside the Hadoop file system. That's also likely. So it's important to check that the interfaces that are waiting for data to be ingested cannot be reached by an attacker, right? And regarding Scoop, as I said, this moves static data. Is commonly used to inject information from different SQL databases into Hadoop. Analyzing a Scoop server, I found an API exposed by default on port 12,000. We can actually abuse it, and we can get, for example, the Scoop server version with this query. And then it's easier to use the Scoop client to interact with the API, because actually there is not so much documentation, and it's quite complicated to use and set up. It took a lot of effort for me to actually abuse this API. So I recommend to use the client. And something important is to download the same client version as the server. For example, this server is 1.99.7, so then we should download the version of the client, the same version of the client from this website. So what can we do? Well, we could, for example, ingest malicious data from a database that belongs to the attacker into the Hadoop file system. It takes some steps. We have to connect to the remote Scoop server, create some links. This is provide the Scoop with the information to connect to the malicious database and also to connect to the target Hadoop file system. And then we have to create a Scoop shop specifying that we want to inject data from this database link to this other HDF link and store it. This is easier to understand with a demo, so let's take a look at a video. Here I have my Scoop client and I have connected successfully to the remote Scoop server. And these are the connectors that we have available. So we need to create a link for the MySQL connection. So I will use the MySQL driver and I will specify the IP address of the attacker machine that has the MySQL database, with I have of course to provide the credential, and it has the malicious data that I want to inject into the cluster, right? And then we need to create a link for the HDF. And here we have to specify the IP address of the name node and the port of the Hadoop IPC. In this case, it's in the port 9000, but it used to be also in 8020 as we saw before. And this conf directory it's going to be the default, it's a remote directory and it's going to be the default path of Hadoop installation. In this case, I'm just providing a path of a desktop machine, but it's going to be the default path for Hadoop. So we have created the links we need, and now we have to create the Scoop shop. So in the shop, we specify that we want to move information from this attacker MySQL database to the target HDF, basically the target Hadoop file system. So here we create the shop, we specify the database and the table from this MySQL database, and there are many values that don't actually need any value, they can be blank. And the output directory is the output directory in the remote Hadoop file system, so that is important. And then most of the other are optional parameters. So here we have our malicious shop, and then it's just about to start it. And that's all we can see from the client. We see that okay, it's what's working, and that's all. So on the other console, I will just log into the machine that has the Hadoop file system just to show you that the data was actually injected. Here we can see that I have two files, one say hacking scoop, the other say hello blah blah. Well, that was the content of the malicious MySQL database that was injected into the Hadoop file system. And keep in mind that you can ingest data, but you can also export, because Scoop allows you to import and export data. So you can do this connection, but in the reverse way. I just specify that you want to export data from the HDF to the MySQL database, for example. So you can either inject malicious data or steal the data of the cluster. Good. So finally, let's talk a little bit about the data access layer. Back to our architecture example, we saw that it's possible to use different technologies for data access. In this example, we are using Presto together with Hive, but there are many others. When it comes to Hive and HBase, these are HDF-based storage technologies, but they also provide interfaces to access the information. So for example, Presto needs the Hive metastore to carry the information stored in the Hadoop file system. So these technologies expose dashboards and interfaces that can be abused by an attacker if they are not rightly protected. Hive, for example, exposes a dashboard on port 10,002, where we can get interesting information and also an idea of how the data is structured in the storage. The same for HBase. And regarding Presto, I found this curious login form where password is not allowed. It's quite curious because it's a login form, but you cannot enter a password. So I know that you can set up one, but by default seems to be this way. So you can write admin user and enter. There is a dashboard that shows some information about the interactive queries being executed against the cluster. So, as I said, these technologies expose several interfaces. It's common to find at least a shared DBC one. For example, in Hive we can find it on port 10,000. And there are different clients that we can use to connect to it, like Squirrel, or even Hadoop includes VLine. We can connect just specifying the remote address. If no authentication is required, there is usually nothing by default. So Hive has its own commands. We need to know them to browse the information. For example, with show databases, we can see the databases on the cluster, select one, and show its tables. And then we have sentences to insert, update, delete, just like any other SQL database. So, I'm running out of time, so some recommendations as conclusion. Many attacks that we saw throughout this talk were based on exposed interfaces, and there are many dashboards that are exposed by default as well. So if they are not being used, we should either remove them or block the access to them using a firewall, for example. If some components need to talk with each other without a firewall in the middle, then we should secure the perimeter at least. The firewall has to be present. Despite the official documentation asks for disabling it, I believe that we can investigate what ports need to be allowed in our infrastructure and design a good firewall policy and rules. So remember also to change all the default credentials and implement any kind of authentication in all the technologies being used. Hadoop, for example, supports authentication for the HTTF. It's possible to implement authentication and authorization in most of the technologies that we have seen. But we have to do it. By default, there is nothing implemented. And finally, remember that in big data infrastructures, there are many different technologies communicating with each other. So make sure that those communications are happening in a secure way. So in the next weeks, I hope I will be publishing more resources about the practical implementation of security measures. So for today, that's all. Thank you for watching my talk. And here's my contact info in case you have any question. Please feel free to reach me out. Thank you. Bye bye.